Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, we'll continue talking about transformers for the third time. What did we cover so far? Self-attention. So we compute dot products between queries and keys, as you see in this figure. Right? We saw this figure before, right? So we do the dot products between queries and keys to get the self-attention weights after, of course, doing the softmax, right? And then with after we get the softmax values, after we get the self-attention weights, we multiply that with the values to get the output vectors, right? Okay, so we call this the self-attention sublayer. And we also saw, I think, last time this in equations. That's the same process. And we went through this example, right? That was towards the end of the lecture, right? To compute the self-attention weights for a specific word. I think we went through that. And we also went through these two questions, right? That was the last thing I think we covered. Right? Any questions before we start? So what will we do today is to talk about some details in the self-attention sublayer, and then we will do some extensions also to that, and then we will see how the self-attention sublayer exists within what we call the transformer layer, and then how the transformer layer exists within the transformer. Okay, and I think this is what inshallah we will cover today. The first thing that we will study today is considered one of the extensions to the dot product self-attention, which is the scaling that we do. So what we have done so far is that we do the dot products between the keys and queries, as you see here. And as you saw last time, this dot product is not bounded. It can be any number, right? It can be very large. What's the consequence of that? If one of the values that we had before we apply the softmax is very large, this will actually dominate the whole values in the softmax, and most of the other values will be zeros, because we even raised these values to the exponential. So the largest number always dominate a lot the other values. So that means that most of the values after we do the softmax will be zeros, which means that we will have very small gradients. You remember back propagation? Okay, if back propagation is a multiplication of values, if these values are very small, then the gradients will be very small, which will make the training very slow. So one way of mitigating this is to scale down these values by dividing by a number. Okay, and the number here is the square root of the dimension of the embeddings. Okay, remember each embedding vector has a length, which is d in what we studied so far. So the square root of d is used to divide all the values before we do the softmax. Type, what's the effect of that? The effect of that is that the dot products will be reduced. Okay, so no one will dominate the softmax. So we will not get as many zeros as we would if we didn't do this scaling. Okay, so this is a small technical detail, but it was proved experimentally that it makes the training much faster. Okay, so that's the first one. And I think did you see this last lecture? I don't remember if we went through it. This is showing you the entire process in one figure. So we start by generating the queries and keys and values. The queries and keys, we do matrix multiplication to do what? Why do we matrix multiply q by k or k by k by q? To get the, no, not yet, to get the dot products. Okay, we scale those dot products, and then forget about this mask, we'll talk about it next lecture. And then we do the softmax, right? After we do the softmax, now we get the self-attention weights, and then we matrix multiply what we get here with the values to get the output, right? So this is the process. Okay, quick question. You have a question? Yes. What's that? Oh, yes, that's what we said just in the previous lecture, in the previous slide. We scale before we apply the softmax. Yes. Okay. Fine. Quick questions. In self-attention, a dot product is computed between which of these? So which one? The third one, a query vector and a key vector. Okay, that's what we said last time, right? Between every query vector and every key vector. Type. Any other answer? No. It's just between a query vector and a key vector. Okay. Type. Which of these are learned parameters? Is it values weights, keys weights, queries weights, self-attention weights, all of them? Self-attention weights only are learned. How about the others? The others are not learned. All of them. The values weights only. All of them. Okay. طيب, let's get back to this figure. Which of these are learned? Now these are the four matrices, right? And in this green block, we have four matrices, right? Right? This is the queries weights, this is keys weights, these are values weights, and these are the self-attention weights. Which of these are learned? Okay, so how about the queries and keys and the values? Are these learned or not? These weights, of course, they are learned, I think, right? So we all agree that these three matrices are learned, right? The matrix, the weights for the queries, the weights for the keys, the weights for the values are all learned, right? These are learned parameters. Type. How about the self-attention weights? Are they learned? No? Why not? Yes, they are computed from these two matrices, right? They are not learned. They are not parameters. Okay, don't be fooled by the word weights. Not every weights are learned. Okay, so yes, so the self-attention weights are not learned, of course. They are computed from the learned parameters, which are the weights for queries, keys, and values. Okay, so what's the right answer here? Oh, not this one. This one. Values, weights, keys, weights, queries, weights, but not self-attention weights. Okay. Is that clear? Okay. Fine. How many parameters are in a self-attention sublayer for a sequence of 100 tokens of 1024 dimension embeddings? So we are talking about the self-attention sublayer now that we studied so far. We have a sequence of 100 tokens, 100 words. Okay. Each token or word is represented by 124 embedding vector. Embedding vector of length 124. How many parameters we have? Why? What are the parameters? Now, to count them, we need to know the parameters, right? What are the parameters? The keys weights, the values weights, and the queries weights, plus also the biases, right? Type. All of these are similar in size, right? They are all similar in size. So let's count for one only, for one matrix and one bias vector. Type. One matrix converts from one embedding vector to another, to the value vector, right? These vectors are the same size, right? What is the size of each of these? 1024. 1024, that's the size of the embedding vector. Okay, each. Now the matrix is applied for each word, shared. It's shared. Okay, so it's applied for each word. Now the size of the embedding vector is 124. So the matrix size is, and the output is 124. So what will be the size of the matrix? 124 square. Okay. How about the size of the bias vector? 124 only by 1 طبعا, right? It's a vector bias. Okay. Okay. So the matrix 124 by 124, right? The bias is just one vector. It's 124 because we convert from 124 to 124, right? Remember this. Let me show you this one, right? Okay, we are converting each vector to another vector of the same size, right? This is the matrix, right? This is the weight matrix. What's the size of this? In this case, 4 by 4, right? Okay, so it's 124 times 124, and the bias is 124 by 1, right? That's for one of them. Then multiply by, we have how many of these? We have 3. 4 keys, 4 queries, 4 values, right? Same thing. So multiply by 3. That's the number of the parameters, right? Yes. Okay. So what is 100 here? We didn't use it, right? We didn't use this 100, right? Yeah, because they are shared. That's the remember in the beginning we said that there is a motivation that the parameters should not increase with the size of the input. Okay, so the 100 tokens here are not we don't care if that 100 was 1,000, was 1 million, the same number of parameters we will have because they are shared. That's one of the reasons actually I gave you this question, to show you that it doesn't depend on the number of tokens. Okay, any questions on that? Was that clear? Okay. Now let's continue with some extensions to the dot product self-attention. We will talk about 2 extensions. The first one is both are actually are important, but this one is really important. It's very important. Positional encoding. What does that mean? So far, when we compute the self-attention weights, does it depend on the order of the words? And when we compute the weights, does it depend on the order of the words? No. If I change the order of the words, I will get the same weights, right? Right? Type. Remember, why are we doing this as a whole? Is process text, right? Right? In text, the order of the words matters or not? Of course, right? You look at these two sentences. The man ate the fish ate the man. They have the same tokens, right? But of course, the meaning is completely different. So we have to reserve the order somehow. So far, the order doesn't matter. But we have to inject something that indicates that this is the first word and this is the word that comes after the first and that's the word that comes after the second and so on, right? This is what we call positional encoding. How do we do that? We do that by adding another vector to the input embedding vector called positional encoding vector. Okay, and you can think of this as a matrix. One column of that matrix is one positional encoding vector for one position. Okay, so the word at that position will have this vector as a positional encoding vector. And if you think about it, if you look at it, you will see that every column of this matrix is unique, is different than the other. Of course, colors here are indicating numbers. Okay, so every column here is different than the others, which means that they are unique. They are unique across the words and relatively similar to the neighborhood. Yani the second one is a little bit of modification over the previous one, and the third is a little bit of modification of the second one. So there is an order between them somehow, but they are different, and that's what we want. We want to add something to the input tokens that will indicate positions. How this matrix is generated? We call it using a kind of time signal function. It's a mix of sine waves with different periods, okay, to give this different patterns, okay, and the patterns are somehow reserving the relative positions, okay, over time. Of course, it's the word here is like time. Okay? Yes. Yes. Indicating the position of the word. Yeah. So here we assume that we have 80 words, okay, and the embedding vector, the D parameter is 64 here. So every positional vector is 64 numbers, okay, and that's added to the actual embedding vector. So this is the input embedding. We'll talk about it in like 5 or 10 minutes, but that's the input to what we studied so far. We add to it the positional encoding vector before going through the process that we studied. So what is the input actually to the self-attention sublayer is the input embedding plus the positional encoding. Okay. That we started with. Okay, we assume that it's there. We didn't talk about how we get it yet. We'll talk about it in like 10 minutes. But let's assume that it is there. There is an embedding vector for each word that has nothing to do with the position. And then we add something to indicate the position. And that sum is the input to the transformer architecture as a whole. But the input embedding we already talked about it, no? No, we assume that it is there, the input. We didn't say how we got the input vectors. Yeah, what we were talking about, like before. Before, we assume that there is an input. Okay, so let me show you. No. Okay, I'm talking about this now. Did I tell you? Did we study how we got this? We assume that it's there. Yeah. This is the input. Now, before we get this, it's this plus the position encoding. Before we do all of that. Yes. Okay. Yeah. Step by step. But now the picture is I hope it's improving. It's extended, but it's improving now. Yeah. Okay. Correct me if I'm wrong. يعني احنا also we add the positional embedding to this input how we calculate. Yes. Before this process. Yes. So it affects this. Of course, yeah. Of course. Before we didn't have any indication of the order. Okay, it doesn't matter. The order doesn't matter. Okay. So you understood this? Okay. So the position in the encoding is the first one. The second one is called multi-head self-attention. You saw this before, right? Okay. In multi-head self-attention, we do that multiple times in parallel. Okay. Same block, of course, with different matrices, of course, with different parameters. Okay, is done multiple times. In the original paper, the number of heads is 8. So this is done 8 times in parallel. From one input, we go through the self-attention sublayer 8 times. Okay. What's the intuition behind that? We'll talk about it, but let's see the process first. So the same input will go through this that we saw before. We get one output, and it's done in parallel multiple times to get multiple outputs. And then these outputs are concatenated together to produce the final output. Okay? Actually, after concatenation, they are multiplied by another matrix before we get the final final output. Okay, so there is another learned weights, which is the concatenation weights, omega c, which is also, and of course there is a bias. So you can think of this as a linear layer that is added after the at the end of the multi-head self-attention, okay, to get the final output. Now there's one small detail. Earlier we said that the size of the input matrix is the same like the size of the output matrix, right? That's if we only have one head. But when we have multiple heads, instead of increasing, of scaling the size of the output, if we do it multiple times, we actually have the size of each head divided by the number of heads, so that when we concatenate them, we'll get back the same size of the input. So for example, if the dimension here is 100 and we have 4 heads, then the output of each head, the embedding vector of the output of each head will be 25. Okay, so 25 from the first, 25 the second, and so on. And then when we concatenate them, it will be back 100. And we have the linear transformation to get the final output. Okay, that's why you can see here that it's D divided by H. So all the weight matrices are D divided by H, not D now. Okay, and the output is D divided by H. That's the length of each embedding vector. Okay. Okay. So first, why you mean why we have multi-head, or why we divide the length? We'll talk about that in the next slide. Okay, but let's make sure that we understand what's going on first. Now, why we divide by the head is to make the size the same. So we don't need more memory when we do that, and that can be done also in parallel. So it's very efficient because all of these blocks are completely independent. They just have the same input, but then all of these matrices are different. Okay. Now, one question: before we do this concatenation, the number of parameters, is it the same like before or increased? It's the same because we divided by the number of heads and then we concatenate. So all the matrices here, if you concatenate the matrices, okay, it will be the same like the matrix, the size of the matrix with one head. Okay, so we didn't increase any parameters here. How about here? Yes, that's a new matrix. Okay, so the increase, the number of parameters that increased is only because of this linear transformation, not because of the multi-head attention. Okay. Yes.
Okay. So for each head, are they different? And how, if they're different?
Yes, they are different because the parameters that are learned here are different. These matrices, so the queries, keys, values, weights, here are different from here, of course. Otherwise, they would be the same.
And the number of heads that we select?
It's a hyperparameter. Yeah, but it's fixed, of course. Yeah. For one transformer, it's fixed. Yeah. Okay, and this is a schematic diagram that shows the process. So from the input, by linear transformation, we get the values vectors, the keys vectors, and the query vectors, and these go through multiple heads in parallel. You can see this like they are in parallel, right? And then these are concatenated, which is here, and then another linear layer, which is the concatenation weight matrix. Okay. Do you see how this is mapped to the process on the left? Okay. Any question about how this works? Yes.
The concatenation of all of the heads. Then, like, we have to.
It's not the concatenation of the heads; it's the concatenation of the output of the heads.
Yeah. When we concatenate them, we have to scale them back to the size of it. No?
We have to.
Like scale it back to the.
They will be because we divide these matrices. the size of them. Remember, earlier it was d by n. Now it's d divided by h by n. So the output already will be like that, and we just concatenate them. When we concatenate them, we get back the same size of the input. Okay, and then we do another transformation together. Okay, after we concatenate, we do another transformation, which is of course learned matrix. Type. Why are we doing that? What's the benefit? What's the intuition? There are two possible intuitions here. First one is that having multiple heads will provide a possibility to attend to different parts of the text. Okay, so for example, one head might do this coreference resolution that we discussed before, the pronouns, which words that each pronoun is referring to. Okay, which is the typical way of the intuition of the attention. Another one might look at the head noun of the sentence. Another can look at the main verb of the sentence. Okay, so getting different ways of relationships instead of just one. And remember that because these are completely independent, it's like we are doing this attention in different representation spaces. Different spaces, we learn different relationships between the words. Okay, so for example, this is the example that we saw last time, right? Remember, it refers more to the animal. That's one head. Another head might do it this way. It, which is the green here, okay? It will refer to tired. That's the verb instead of the noun, okay? So different ways of attention that can help the final output embedding vector. Okay, so that's the first intuition. The second one is that this will avoid bad initialization. If we do it just once, we might be stuck in one bad attention representation. Okay, so doing it multiple times will give more chance to avoid this bad initialization. Remember, all of this is initialized randomly, right? All the weights. So if it's initialized in a bad region in the space, we might not get what we want. Okay, so giving it more chance to avoid such initialization problems. Okay, yes. Yes. Yeah. By training, overtraining, of course. Now, we didn't talk about training yet, okay? But this is not by chance, it's by training. It will see so many input sentences and text and documents so that it can learn these things. No, not always. No. Every head will learn something different. If it is initialized with different weights, of course. If it's initialized with the same weights, it will learn the same thing. That's why we have multiple of them, and they are running independently. Okay? Yes. To learn more about the context of the input. Yes. To make different or more meaningful connections between the words. Okay? But they are not preset. We don't know in advance what will happen. This is by training. Overtraining, it should learn something useful. Okay, and let me tell you also, if sometimes we might look at this self-attention weights and we might not understand what it means. It can happen, but this is what was learned through their training examples. Okay, and of course I'm showing you here good examples, right, that can be understood by us. Will the process be faster here? It will be slowed down a little bit just because of this concatenation, because all of this are done in parallel. All of that is done in parallel. So if I have the power, if I have the parallel processing architecture that can allow me to do that, then it won't make more time. It won't need more time, except that this concatenation, and this is nothing. If we have the same input, different parameters, different weights. Okay, these are different weights. So each one will learn something different. No, are they fixed weights? We learn them. Of course, after training, they are fixed. Okay, but we learn them. It's like learning the attentions from different perspectives. Okay, fine. Is that did I answer your question? Okay. Okay. Any questions so far? So are you ready to see where is the self-attention in the transformer layer? We talked about self-attention as a sub-layer, but it's not the only thing that is done in the transformer layer. Yes. Okay.
Okay, so when we have different heads, like the process between having one head and different heads, what if like adding more heads, like all the ones that we added, were actually a very bad representation?
It depends on learning. We will train this model with very large number of sentences and very large documents. I mean, it will be chunked, of course, but billions of words at least. Okay, books with pages, essays, whatever you can think of that is accessible to whoever is training this model. Okay. Okay. Any other questions? This is massive. It uses a lot of data, so that it can learn that number of parameters that we will see. Actually, in the question that was about the number of parameters, if you notice, we said that it's 124 by 124, right? That's one metric. What is 124 by 124? It's a million, right? It's million, just one matrix. Okay? This matrix only is million parameters. Okay. If of course if the dimension is 124.
But when we have different heads, it's not.
Yeah. But this is just one sub layer within one layer within the. Okay. So we are extending now. That's not everything. That's just the self-attention. Now, where is self-attention in the transformer layer? Here it is. Where is it? It's just the orange part. Okay, but of course it is the core component. Okay, you will see that the other components are really straightforward. They are not that complicated. Type. Let's see what is going on here. We have this input as usual, right? This is the input embeddings for the sequence, for the input sequence. It will go through the multi-head self-attention. So all of what we studied so far in transformers is inside this box, right? Right. This is the multi-head self-attention. That's the 2 lectures before and today's lecture. Okay. Then the output of this is added to, again, the input. For some reason, we'll talk about it, but this is the process. Okay, we call this residual connection. So the residual connection means that we add the input again to the output. So now the input to this part is the output of the self-attention plus the input of the self-attention. Okay. Then this input goes through what we call a layer normalization. It's a normalization process. We'll talk about it. Then it goes through fully connected neural network. This is the rest of the course that we studied. Okay, this is before transformers. Okay, this is the fully connected layer, fully connected network. We'll talk about what it means exactly. Okay, but this is the standard neural networks that we studied. Then this output is added again to the output of this, going through another layer of normalization, and that will provide the final output. This is one layer of the transformer. Okay? Right. Now let's talk about each one. Let me talk about each one and then we'll take your question quickly. Right. These connections, as you see, it's just adding the input back to the output, right? What's the intuition here? What's the point here? Remember that this is just one layer in stack of layers. You will see that the transformer actually has a stack of layers. When we have deep network like that, remember backpropagation, the gradients go backward, right? If we have very deep network like that, as we move from one layer to the other, probably the gradients will get smaller and smaller. Okay, so it will not reach a lot to the parameters that are early in the network. To try to overcome that, we do this skipping connections. Okay, so skipping connections allow that the gradient don't be only from that path, but also can be from that path. So the gradients go back to the whatever the parameters here before that, so that it will make the training faster. It's only for the objective of making the gradients flowing back faster to the parameters when we have a stack of layers. Okay, it's skipping because it's kind of skipping this part. It's not skipping overall, yeah, but it's called generally skipping connection because it's skipping this whatever it's like bypassing part of the network. No. In the backward we use all of them, but the gradients will be from this and that instead of this only. Okay, so it won't be that small. It will bypass more components, so it won't get that small. Okay, you got that? Okay, and same here, same idea here. Okay, type. Now this normalization is also done experimentally. It was shown that by this normalization also the training will be faster. Okay, we'll talk about exactly what the normalization that is done here. But normalization means you get some numbers, you normalize them, you convert them by some transformation to another numbers within some range or with some properties. Okay, and that's done here after the self-attention sublayer and done here after the fully connected network component. And one important thing about the network here, about this network here, is that you can see them like they are going in parallel, right? Actually, this is one network that is applied to all the vectors, shared exactly with the same concept like the matrices that we saw in the self-attention. Okay, so it's one network, one small network, one actually not very small, but one shallow network actually, as you see, that is applied, same network applied to multiple vectors, to every vector, every output vector. Okay, and that's why they are in parallel. They can be done in parallel. There's no dependency between them. Okay, so that's one network that is shared among all the output vectors here. Okay, type. This is just showing you the process in equations. So x is the input here, plus what is this? Multi-head self-attention of x. And this is back to x. So that x now is this. Okay? And then going through layer norm, which is the second equation here. Then each vector, that's why it's x small now, n, which is one a vector for one word, is going through MLP is multi-layer perceptron. This is another name of fully connected network. Okay, so that's a fully connected network with input the input only the vector of one word, and again, this is residual, so it would be added back. Okay, so just a second. So this is the process here. Okay, and then the output of this is going through the layer normalization, which is this. So we'll get the output from here. Okay, yes. You had a question before.
Now I have three.
Okay.
Okay, the first one is the positional embedding. It's not done here.
Where is the positional embedding here? It's not shown here. Where is the positional embedding?
Before the manual
This is the output or after the positional.
So it's not in the transfer.
Yeah, the positional embedding is somewhere here. It's not part of the. No, it's not part of the layer. It's done once. Yeah.
And is it learned?
Okay, very good question. There are two implementations. One that is fixed, static, and another is learned. So it can be learned also, yes.
Neural network. Yani, what's the point of that?
Why is it parallel, you mean?
That's the second.
Okay. Right. And I can answer this parallel thing, because we want the parameters to be shared. Okay. So we don't want the parameters here to increase as the sequence increases, right? Like what we did in the self-attention. Okay. So we want this to be parameters that are shared among all, and that will also make it efficient, because we can, if that's the case, then we can run it in parallel. Okay, and that's a kind of transformation from whatever we have here before we get the final output. It's another set of parameters that can help training. It's another transformation. It's like any neural network that we studied before, right? It transforms from one space to another. Okay, it will be learned in the training process, but I don't have a clear intuition about why is that. And why this is taking me, before I take your question, this taking me to a point here, that how did we get this design? How those people got this design? It's just by revelation that, okay, here is the transformer layer. It starts with the self-attention, and then this, and then this, and then this. Of course, by experiments. Okay, maybe started with self-attention only. Even the self-attention was experimented to get all of these details, and then by adding this, they showed that the performance improved. Okay, why don't we add it again, and why don't we add a fully connected, and so on. So these things are step by step, are incremental. They don't come just by revelation like that. Okay, yeah, it looks now complicated, but it was simple at some point. And it will be more, but you can see that now there are blocks. Yani, imagine that the whole course now is in that block, right, before transformers, right? Okay, and I don't have to say what is this now, right? So that's the whole course. The last two lectures are now a block like that. So when I tell you now that this layer is repeated 8 times, you will not tell me, oh, what is that? Okay, you know now that this is one, it's repeated just 8 times, right? So so it will be, yeah, if you look at the final product, you can think of it as very complicated, but it's a collection of small things. Yeah, we'll see that. Okay, we didn't talk about that yet. We'll see it. You still have a question, or done?
No, it's not a question, but it's more of the parallel neural network. It's actually, you mentioned that it's a shadow.
Yes, it's just one hidden layer.
And the perceptor has like the neural.
No, forget about this name. This name is historical. Okay, the fully connected network is called multi-layer perceptor in general. Forget about that. It's just a historical name. Because every neural node is called perceptor. Okay. Again, similar to what we just mentioned, neural networks, when it was introduced by one node only, which was called perceptron, and it was a breakthrough. Okay, one node, and then we have layers, and then we have multi-layer perceptron. So That's how the name came. Okay, but it's a shallow network as in our terminology. Okay, so this is a very important point, that these are shared parameters. Okay, right. Now how the normalization is done very quickly. We get the input here. Okay, it's embedding vectors for all the tokens. Okay, we compute the mean of them and the standard deviation and apply this to the values. The goal is that after we do this normalization, after we do this step, all the values will have a mean of 0 and standard deviation of 1. Okay, so any outliers or any extreme values will be a little bit bounded. Okay, so after this, the value minus the mean over the standard deviation, then the values all will have mean 0 and standard deviation 1. That's a statistical operation that is very well known. And then each value will be scaled and shifted. If each single value will be multiplied by a parameter and added to another parameter. Okay, so these are two trainable scalar parameters bear every unit, every value of the output vector. Okay, so from here we started with a matrix, right? Here we have another matrix, right, with the same size. We will get the mean value of that matrix, the standard deviation of that matrix. We do this transformation and we get back another matrix that is normalized now. Okay, and this normalization was shown experimentally to produce faster training. Okay, so this is what we call layered normalization. Any question about that? So this is adding parameters. Okay, so there's two parameters for each of the output values, not vectors, values, single values. Okay, so that's the layer normalization, and then the fully connected network. I think you are very familiar with that. This is just one hidden layer, as I told you. It's shallow network. What is this? What's the input here in our context?
It's like the input and output to the multi-head, right? Like that layer.
So what does that represent
This
in our context?
output and the input, like let's say it's the
Yeah, whatever the output of the previous process. Yeah, but is that for everything or for one word? For one word? Okay, let's get back to here. What are these arrows? These are vectors for different words. So every vector of one word is going through the network.
It's going through all of the network.
No. It's okay, this is the same network repeated multiple times. It's shared like the matrix. We multiply the values matrix by every word, right? By every vector of the words. Okay, that's the same thing here. Every embedding vector of one word, the embedding vector of one word is going through this network. The second one is going through the same network, and the third is the same, and so on. Okay, it's one network. It's shared. That's why we said it's shared parameters. Yeah. So here, this is the embedding vector of one word going through the hidden layer and then back to the same size, right? Back to the same size. So this is D. This is another dimension. Usually it's bigger, and then the output back to the same length. Okay, and I think you can understand this now, right? What is this? Let's say that the input is X. It's multiplied by W1. What is W1? I understand. Where is it in the figure? This part, right? This is W1, and B1. What is B1? Biases for the hidden layer, right? And what is this max 0? The radio function. Okay, the radio function applied to the output of the neurons. And what is W2? This second weight matrix. B2 are the biases of the output. Okay, so that's the fully feed-forward network. FFN means feed-forward network. And we can also see it that way. We have linear transformation, which is this, followed by activation, the radio, and then another linear transformation, which is for the second part of the network. Okay? Yes.
So for the parallel neural network,
Yeah.
we have
It's this network applied. Yeah, we are changing the input. It's the same network, changing the input.
بس احنا like we have of that network the number of words.
Exactly. Number of words in the sequence.
Well,
Yeah, but they are not different. It's the same. It's shared.
and the initialization is going to be the same of the weights of the parameters of each network. Yeah.
It's one network. It's one network.
But it's going to be get trained, no?
It's one trained network.
Already.
Yani already. It will be trained, but it's one.
But for each
It's like the remember the values matrix.
okay.
It's one matrix, right? But it is applied to all the vectors. Same here. Now this is also a matrix, by the way, but multiple matrix in a network. Okay, this set of parameters are shared among all words. So this same network is learned, but it's just one network that will be applied to all the vectors of the words.
It's learned previously or it's learned
What do you mean by previously? During training. We didn't talk about training yet, but that's the architecture, right? We will train it at some point. We are talking about the architecture now, right? It's like telling you that this is previously. We have multiple hidden layers, and each hidden layer, we are specifying the architecture now, but all these parameters will be learned.
right now we're talking about the architecture.
Yes, yes.
Okay, but it's stuff that is already there. Yani each neural net like
We didn't talk about the data that we'll use for training yet, or how the data will be structured. But yes, we are talking about the architecture.
yeah,
Just assume for now that these things are trained.
حتى
Everything.
self-attention, the self-attention
ما هو trained already خلاص trained. Yeah, this is how it would work. But that's the architecture. Yeah.
why training this like
Network,
the
this
different
model.
parts before that?
Yeah.
Does each process before affect the other one?
Okay. We'll talk about it when we talk about the transformer. Yeah. Of course. We'll talk about that. Okay. Type. Any questions so far? Transformer layer now, right? Now you know what the layer has, right? Type. Let me ask you one quick question. What is what's the input and what's the output now? We didn't talk about layers yet. Okay, it's one layer. What's the input to the layer and what's the output to the layer of the layer? The input is the embedding vectors. What's the output?
It's an embedding.
Another representation. It's embedding. Of course, the positions is done before that. Okay, it's done before that. Okay, so you can see the size of this is the same size of this, right? Okay, so it's just that it has better representation now. Okay, fine. Okay, fine. And in the beginning of this transformer session, I told you that it was designed to process text, right? And it is very motivated by natural language processing. So let me talk about this a little bit because it has the beginning part of how we process the text and to get it as an input to the transformer. So how that is done. Okay. First thing, we are given text, right? But I told you that these are words or tokens. How do we get these tokens? Okay, we get them by a process called tokenization. Okay, tokenization means splitting the text into small units. These small units are called tokens. Okay, there are many issues of that. Which tokens? What is the unit that we should use? There are so many issues in this. Here are a few of them. For example, these words should be the same token or different tokens. Walk, walks, walked, walking. Or this should be the same token when we split the text. Should be the one token or different tokens. Remember that they are related, right? So should we represent each as separate token or the same token? It's not clear how to deal with punctuations. Should they be separate or they should be part of the word? How about words that don't appear in training, like names, new names? Okay. Um, if we train by specific tokens and then we see a token that a new name or a new word that was not seen in training, what should we do with it? So there are many issues with that. Okay, it's a big topic in natural language processing. One very common solution to that is called subword tokenization. So instead of taking complete words, we will get parts of the words. Sometimes it will be the full word, sometimes it will be part of the word. We call this algorithm subword tokenization. Quickly, how subword tokenization works. Let's say that this is the text that we have. Okay. Of course, this will be done on very large amount of text, lots of text. Okay. But let's assume that lots of text is this. It's like a song, I think here. So the algorithm starts by representing each letter as a token and counting how many times each letter appeared in that text. We call this the frequency of the token. So you can see that table, this row are the tokens and this row are the frequencies. So for example, the letter A appeared 12 times in this text. Okay? And then it will combine together two tokens that appear adjacent in the text the most. The two adjacent tokens that appear the most among all adjacent pairs of the current tokens. Okay, so if we do that on the text, we'll find that the most pair is SE. Okay, so SE actually appeared 13 times. So we will combine S with E, but of course S and E doesn't always come together, right? So 13 times they come together, but the rest of the times they don't. So we will add the new token, which is SE now, to the list of tokens, but still we can keep the others because they don't appear always together. So if you see here, E appeared 28 times, right? It appeared with S 13 and without S 15 times, and so on. Okay, so we will add new token and then reduce some number from the frequencies of the combined tokens. Of course, within this process, one token might disappear completely because it's always appear with the other one. So the frequency of it alone might be 0. Okay, but in the beginning, we will add tokens, and that will repeat by over iterations. So every iteration we combine two tokens into one. Okay, so after some in the second step, you will see that we combine E and space. The underscore here is a space. Okay, so E and the space was the most common, so we'll add it, and so on. Every iteration we combine two adjacent tokens. So what is the intuition of that? We are trying to see what are the most frequent part of the words. So we are trying to capture the main patterns in the text. So if we do that more times, you'll see that we started to get complete words like could, like had. Okay, if we do it extremely, we get just the words. Okay, so when we start, that is the number of iterations, and that's the number of tokens. You will see that the number of tokens is increasing. At some point, it will decrease again because the smaller tokens will have very small frequencies up to zero, and when they come to 0, they will be removed. Type. Which tokens we will get at the end? It depends depending on how many tokens we want to keep. Okay, so if I have a specific number of tokens that I want to keep, then I will stop when I get that number of tokens. So for example, let's say مثلا we want to get that number, that's I think in thousands, maybe I don't know, 25 thousands, I can stop here or here. Okay, So to get, so this now will be the tokens that the system will understand, will see, will use. Okay, so that's the tokenization part. Any question about that? Yes. Yes, the number of tokens. That's a hard question. We don't know, but we at least we know how many tokens we want to keep. So once we reach that number, خلاص. And I want the vocabulary. This is called the vocabulary that the model will understand. Okay. Of course, as I increase the vocabulary, the parameters you will see that the parameters will increase a little bit. Okay. So it's like a budget. I have a budget for 20,000 tokens. خلاص, I will stop at 20,000. If of course more will be more flexible, but not that much. So there's no answer to this. There's no one gold answer on what number is good. Okay, it depends on the domain. Yeah, maybe the domain I'm only training this model for the medical domain, مثلا. Okay, I have a knowledge, a prior knowledge that the vocabulary in that domain is around 10,000. Arabic might be different. English might be different. Okay, if I am training that, because this is like training, right? I'm training a tokenizer. If I'm training that on multiple languages, and we can see now ChatGPT, for example, is multilingual, right? How does it understand different languages? Because it was trained on data that is multilingual, right? So the tokens that it can understand comes from different languages. I can put now documents of different languages and learn the tokens together. So I can now my vocabulary will cover multiple languages. In this case, I think the vocabulary size should be increasing, right? So it depends on the domain that you have. Okay. Now we understand this tokenization thing. Okay. Now let's say that now we will understand how the input embeddings will come to reality. Okay, because we assume that we have input embeddings, right? Okay. So how do we get that? We have a sentence like that. We will tokenize it using the tokenizer that we learned in the previous slide, right? So which tokens we will get. Assume that here that the tokens are the full words, just for simplicity. Okay. So here we have how many tokens? 5. So what we will do first is we have now the list of vocabulary tokens, right? Let's say that we have 30,000 tokens. The vocabulary size is 30,000, which means that we have 30,000 different tokens possible in the language that we will handle. Okay. Each of the tokens we will give it a unique number from 1 to 30,000, just an index. Okay, يعني مثلا the word an is 8, the word 8 is 17 or 100, whatever. Okay, each word has just a unique ID. Okay, and initially we will represent each of these tokens by a vector. We call it one hot encoding vector. One hot encoding means that the vector will be all zeros except 1 in the position of the ID of the token. Okay, so for example, this is 5 because we have 5 here, right? So the word an, let's assume that it has an index 1, 2, 3, 4, 5, 6, 7, 8. So the vector for an is all zeros except 1 in the position 8. And you can see that even here because an appeared twice here. Okay, so the other an also has the same representation. This is called one hot encoding. Okay, everything is 0 except just 1. So this is the very initial embedding, by the way. Okay, which is meaningless, right? It doesn't capture any relationships, right? It's just random ID for each word. خلاص? With me so far? So what is the size of this matrix? The number of the size of each column is the number of the vocabularies, vocabulary size, number of tokens, which is 30,000 in our example. Okay, and the number of columns is the number of tokens that we have in the sentence now, in this sentence. Okay, right. Next, we will multiply this by what we call an embedding matrix. In an embedding matrix, these are the real embeddings. Okay. In this matrix, each column is the embedding vector for one token in general. So the number of columns here again is the number of is the vocabulary size, is the 30,000. Okay, and the size of the column is the dimension that d that we used before, the parameter d. Okay, which is the dimension of the embedding vector. Okay, which is whatever, about 512 or 1024, whatever. Okay, type. When we multiply this matrix by this, it's like we are indexing for the right words. Yani here, this is n, right? When we multiply this column with this matrix, we will get the corresponding embedding vector of n, which is number 8 here, this one. Okay, and for the second one, because this is just one here, all of them is zeros, so it will cancel all the others except one. Okay, and the second will get the vector for aardvark. I think this is an animal name. Okay, aardvark is this one. Okay, and so on. So if we multiply these two together, we will get just the embeddings for the tokens of this sentence. And if you look at the colors here, you will see that this is exactly the 5 columns corresponding to the 5 embedding vectors of these 5 tokens. Now, this is X. We will add back the positional encoding to it, and then it moves forward. Okay? Now, how do we get this? We call this the embedding matrix, right? And this is now the embedding, the actual embedding input that will go to the transformer. But how do we get this? This is just a revelation that this word has this embedding vector, and this word has this embedding vector. How do we do that? No, it's just learned. These are new set of parameters. Congratulations, we are adding more parameters to the model. This matrix is learned parameters. All of these values are learned, are trained. With all the examples that we will apply to the network in training. Okay, billions of examples we will use so that we can get embedding vectors that are good to be used. Okay, so this will be done even before the layer that we talked about, right? Because with the input to the transformer layer is the embedding vectors, which is this. And this comes from the one-hot encoding, which is the very simple, naive embedding. Okay, very naive, taban. It's just 1, 1. And it is just, it's like selecting which embedding vectors, okay, from that matrix. And that matrix is actually part of the model now. Okay, so you can think of this as a layer, embedding layer. Actually, it is called embedding layer here, right? Yeah, I think if we go to here, yeah, input embedding. That's a layer. Okay. Now from that we have the embedding vector for this sentence, and we add the positional encoding, and then now this is X. Okay, and that part is learned. It's a layer in the whole architecture that is learned. Okay. Now, what is the model? Okay, so we saw the layer. Okay, what is the model? The model actually is a stack of these layers. This is from the original paper. It looks very nice, right? It has 2 parts. Forget about the right part now. Let's only focus on the left side. Okay, what do you see in the left side? But it's vertical instead of horizontal, right? It's exactly the same things that we studied, except that it's now vertical instead of being horizontal. Okay, so that's one transformer layer, and we have n of them. N here is not the input sequence. N is the number of layers here. Okay, so in the transformer layer, they started with 8 layers. So we have a stack of 8 transformer layers on that side. Forget about the right side, we'll talk about it inshallah next lecture. Okay, but for the left side, it's a stack of 8 layers. Like, what does that mean? When we have layers like that, the output of one layer is the input of the next layer. So the output of the first layer, input to the second. Output of the second, input to the third. Output of the third, input to the fourth, and so on until we get to the last one. Okay? So that's the stack. We call this encoder. We'll talk about that inshallah next time. Okay? So that's the طبعا very similar. Also the right side also very similar, except that we have one more component on the right side. Okay, we'll talk about it next time. Okay, but it looks very similar. So it's a stack of layers, and the output of one layer is the input to the next. Now, if you look at the 8 layers, or whatever the number of layers, what are we doing? What's the input and what's the output of these? The input is the sequence of text with embeddings, like what we saw in the previous slide, and the output is also embeddings. Okay, it's also embeddings. Okay, we didn't do anything yet. We didn't do any application. We didn't do any specific test. It's just another representation, but it's much better because it's going through this attention multiple times at multiple levels. Okay, so this is called representation learning, by the way. We are learning representations here. We are not doing any specific learning task. We are just learning better representations of text in this case. Okay? Is that enough for you today? I think so. Okay. So inshallah we'll continue next time. Assalamu alaikum wa rahmatullahi wa barakatuh.